Different classifications of reactions might actually apply to the same reaction, so try to use your judgment and answer whatever question I might ask with the best answer that's available. Some reactions are called acid-base reactions. Others are precipitation reactions where the reactants start in the solution phase and end up precipitating out or making a solid crash out. So there's junk in the bottom of the flask when it was just a nice homogeneous mixture before it was a solution. Redox reactions can be classified in different ways. Combustion, where oxygen gas is one of the reactants. Synthesis reactions are where the reactants combine to form bigger, I guess more complicated structures. And decomposition reactions are where the reactants get broken up into smaller pieces, including element products. So we'll kind of see some of this. So I'd like to talk to you a little bit about what acids and base reactions are. And there are different definitions for what acids and bases are, but in this class, this definition will go pretty far. Acids generate H plus or H3O plus in water. So if you look at this diagram, it's color-coded. The HA, this generic acid we're calling it, it could be like HCl or HBr or something. It ends up giving up a H plus ion to water. So the water now has an extra proton, and the HA molecule has effectively given up an H plus, and it leaves an A minus in solution. So the bottom line is an acid, according to the Arrhenius definition, is something that gives up an H plus to the solution and generates H3O plus in water. So if you see this kind of stuff, you should think acid, right? You should go, oh, wait a minute, it's generating H3O plus. What generated it? The acid. Bases generate OH minus in water. So if you think of this reaction, ammonia plus water, ammonia removes an H plus from water to make OH minus, and it has given this cationic species that has taken up the H plus from the water. So if you see something that generates OH minus, it's a base. That base reacted with water to generate OH minus. So this should seem pretty straightforward. It can get kind of complicated, but the simpler ones are pretty good at following this. As you continue your chemistry careers, we'll learn additional definitions that are a little more complete than this, but this works for identifying quite a few acids and bases. So acids and bases can be strong or weak. And what that means is that a strong acid will do that reaction. It'll give up an H plus to form H3O plus in water to completion, meaning that like you don't have to worry about there being any HA left over. So it's kind of weird that we're talking about this before equilibrium, but just like everything else in this class, there's not a good place to start. So we'll just jump in. So like if we added HCl to water and you wanted to know how much acid, how much H3O plus is in the solution, you would just assume that all of it reacted. And that's a pretty good estimate. You can also say the same about bases. Some bases are strong bases, meaning that they generate OH minus for every molecule that you add of the base. Like there's none of the base left. It just completely turns into OH minus. It does this reaction all the way. There's no ammonia left. It all turns into ammonia. As it turns out, ammonia, sorry, the ion is ammonium, my mistake. Ammonia, NH3, is actually a weak base. It doesn't go to completion to NH4. So you could say that an acid is stronger than another acid, but that would just mean that more of it goes to completion, or that it's able to protonate a base of the other acid. The bottom line for now is that I want you guys to kind of know what an acid-base reaction looks like, that this is an acid because it makes H3O plus by giving up an H plus, and that this is a, did I say base or acid? Sorry. This is an acid. And then this is a base because it takes an H plus from the water and generates OH minus. So what does an acid-base reaction look like? Here's an example where if you add an acid and a base together, you end up generating just a salt and water. Because one of these gives up H plus and the other one gives up OH minus. So that's going to give you just net water. We could write a complete ionic equation for that. And we started talking about this last week. If you strip away the ions that you start with and that are also there at the end in solution, those are called spectator ions. If you get rid of those and just look at what changed, those are in the net ionic equation. So you get the idea. You see an H, you see an OH minus. That's probably acid-base, and we're going to probably come back to this several times in the remaining weeks. Oxidation reduction reactions, what do they look like? They look like something is changing charge. Some element's charge changed. And that's just the movement of electrons. And we'll look at this in a second. So, for example, you could think of sodium metal and this sort of mythical chlorine ion reacting together to form sodium plus and chloride minus. So that means that like the chlorine would lose a electron, and the sodium would lose an electron and give it to the chlorine. So the sodium would have a +1 charge, and the chloride would have a -1 charge. So the chlorine atom would gain an electron, it would be reduced, and the sodium atom would be oxidized. It would lose an electron. One of those in there. So Leo says GR, loss of electrons is oxidation, gain of electrons is reduction. The electrons have to go somewhere, they don't just magically disappear. So wherever there's an oxidation, there's also a reduction. For someone to lose an electron, somebody else has to gain an electron. Yeah. But the key here is that, hey, look, sodium has a change in charge. It either lost or gained electrons, and chlorine either lost or gained electrons. That's how I know that this is an oxidation reduction reaction. So the magnesium loses electrons, it gives up electrons to oxygen, so the magnesium gets oxidized, and what happens to the oxygen? Does it get oxidized or reduced? What do you think? Does it get oxidized or reduced? Okay, next person. What do you think? Does it get oxidized or reduced? Any? The person in front of you, actually. Yeah. Does the oxygen get reduced or oxidized?
No.
Magnesium got oxidized.
Oh, okay.
All right. So this is.
So this is this.
Yeah. Okay. I was going to go in order, but you're up next.
Oh.
I can never hit these things. So. Like, yeah, I'll break one of them now. I don't know. Hulk smash. All right, so yeah, this is just more examples of this. Okay, so if the aluminum loses electrons, it goes from a 0 charge to a +3 charge. Is it getting oxidized or reduced?
Getting reduced. Right? Reduction is a loss of electrons?
Reduction means a gain of electrons.
Okay.
It's confusing. That's why people came up with the mnemonic. And oxygen gas tends to get reduced. So even like thinking about oxygen versus oxidized, that won't help you either. So yeah, here the aluminum reduces the iron. The iron gets reduced, but the aluminum gets oxidized. Right? Is that cool? All right. What's next? Who can tell me whether or not is copper getting oxidized here, or is it getting reduced? There's only two answers. What do you think? What do you think? Yeah, the copper is getting oxidized, yeah. So if there's no charge on an element by itself, like aluminum, if somebody says aluminum or aluminum zero or aluminum solid or aluminum metal, all those things mean the same thing. It's aluminum with exactly the same number of protons as electrons. All right, so it doesn't have a charge. If I look over there on the other side in the products and I see aluminum oxide, so it's 2 aluminums, 3 oxides. Each oxide has a -2 charge because I can look it up in the periodic table. It's in the column that's 2 over from the noble gases. And that means each aluminum has to have a +3 charge. And it's also in like the column that's like 2, I guess 3 over from the noble gases. So it's a metal and it's going to lose 3 electrons. So I know that aluminum has a 3+ charge. Just to be as clear as possible, I really want you guys to be able to tell me what the charges are on every one of these elements in here. But let's say that you get that down pat. Let's talk about the electrons moving. So in this diagram, aluminum is 0 over here. Like there's no charge on it, so it has as many electrons as it has protons. The little arrow shows that it loses 3 electrons, and actually over here you see a 3+. So how do you get a plus charge on an ion? That means that there was a loss of that many electrons. That's the hard part, honestly, is keeping the signs right in your head. So, or at least for me anyway. So loss of electrons means you add to the charge. So yeah, I mean, you're on top of that. So, you're like, yes, moving on, all right. So yeah, that's how I know that it lost electrons, is because it had a 0 charge here, and then it has a +3 charge here. So that means it lost 3 electrons. For iron, I know that iron had a 3+ charge over here. It has a 0 charge over here. That means it gained 3 electrons. So it had a change in charge of -3. That means it gained 3 electrons. How about these oxygens? Did these oxygens get reduced or oxidized at all? No. They didn't. There was no change in their charge. So yeah, that would be a great question, actually. I should probably use that as a clicker question or something. But yeah, no change in charge. There's no oxidation or reduction. So this whole reaction is an oxidation-reduction reaction, but that doesn't mean that everything has a change in charge. It only really takes one thing, or I guess one pair of oxidation reductions to make it an oxidation-reduction reaction. There can be other things around that don't change.